All right, so in this example, we're again going to do this kind of full gamut of a whole bunch of things. So we're going to start this thing off by showing that two numbers are in fact relatively prime. Once we do that, we're actually going to run this extended Euclidean algorithm to actually try to find those special little numbers x and y that are going to give me this equation of 26x plus 19y is going to equal 1. What's going to happen is that after that, we're going to use that new special little equation to actually create some inverses. And then once I have those inverses, I'm going to go ahead and actually attack one of these congruences. So in this case, I'm going to try to solve one of these things. So first things first, we're going to show that 26 and 19 are in fact relatively prime. In this case, you could probably look at these two numbers and actually say, okay, they don't actually share any divisors other than 1. So hey, I know that they're relatively prime. But knowing that I'm going to want to find those little special numbers x and y, I'm actually going to attack this thing using this Euclidean algorithm so that I'm actually able to backfill this thing and find those little things via this extended Euclidean algorithm. So in this case, we better kind of see those little ones emerge at the very end, which is kind of a nice little check as we go. It's also good practice to run this Euclidean algorithm a couple more times at least before you kind of get really sick of it because you're losing little negative signs and all these little plus signs as you go. So in this case, I want to start this thing off by actually asking how many times does 19 go into 26? Well, in this case, if you simply do that division, you're going to see that you have a remainder of 7 because 19 is going to go into 26 one time. So in this case, what I end up with is a 26 is going to be a 1 with that 19, and then here's my little remainder of a 7. We know what's going to happen in this situation. We're going to take that little divisor of 19, and I'm going to pair it with that new kind of remainder in this case, and that's going to become my new pair. So I'm going to have a 19 and a 7. What's going to happen is that that new pair is going to jump over here, and then I'm going to run this division algorithm one more time. It's just going to keep on going all the way until I get to a stage of having a nice little remainder of a 1, and that's going to be my relatively prime indicator. So in this case, the 19 and the 7, I know that 7 is going to go into 19 two times because 7 times 2 is 14. So in this case, I'm going to have 19, the 2, that's 7, and then I'm going to have what? A remainder of a 5 because I said that's a 14, and that's going to make my 19. So my new pair is going to be a 7 and a 5, and then I run this thing one more time. So the 7 and the 5, and then I'm going to see, well, 5 goes into 7 one time because I'm going to have a 1 times a 5. I'm going to have a little remainder of 2 in this case. My new pair is then the 5, 2, and I go back over here and do it again. So 2 in this case is going to go into 5 twice, so I get 2 times 2 plus a 1. And hey, there's what I'm looking for in this case. So I'm going to have my 2, 1. And if I wanted to, I could run this one more time to really see that nice 0 emerge. So in this case, 1 goes into 2 times because 2 times 1. And then here's my remainder of 0. So again, if you're thinking about this from a coding side of things, that's going to be the indicator of, hey, you're going to stop at this stage and you're going to look for that last non-zero remainder. Officially, if you ever see a 1 in this case, you know that that's going to be the last non-zero remainder because that next step is always going to bring about a 0. So in this case, yep, we do in fact have that these things are relatively prime because they have a GCD of 1. So in this case, if I look at my at least somewhat more filled out notes of these things, you can see that I got the exact same thing. So yeah, I actually did my computations correctly. The next step, hopefully I can do correctly as well. There's a bunch of negative signs that come into play in this next little bit, but we'll give it a shot as we go. So our next step is going to be, I want to find integers x and y, so there should be a little y after that one, that are going to have this special property that 26x plus 19y is in fact going to give a 1. So what's going to happen in this case is I'm going to take this little 1 that I have at that last step, or at least the second to last step, and I'm going to try to work backwards. So the Euclidean algorithm goes this way, and then this extended Euclidean algorithm is going to run in reverse. So I'm going to take that little 1 and I'm going to solve for it. So in this case, what I end up having is I'm going to have a 1, which is going to be that 5 minus a 2 times a 2. What's going to happen here now is I'm going to work to slowly kind of reproduce these new objects via these little remainders. So you can see that in this process, that little 2 emerged, which is exactly going to be that 2 that came from that remainder from the step before. Because we know that these things are always going to shift around as I go. You're going to have that 7 is that 7, that 5 is that 5, that 2 is that 2, that 1 is that 1, and that 1 from there. So like I said, every time you backfill, you're going to have that previous remainder making an appearance, and you're going to solve for that new object. So in this case, what's going to happen is that if you take this equation and solve for 2, you're going to have 2 is going to equal 7 minus 1 times 5. And that's going to be the bit that I'm going to substitute in. So in this case, what I'm going to have now is a 5 multiplied by a 2, and then here's where that 7 minus 1 times 5 is going to come into play. Next, I'm going to distribute that little negative 2, so a 5, there's going to be a negative 2 times a 7. The negative 2 and the 1, that's going to create a 1, and then I'm going to have my little 5. I'm going to loop, you're going to kind of group these little things that have 5s together. So in this case, I have 2 of them over here, and I have 1 of them officially over here. So I have 3 5s and negative 2 7s. So now I'm at the stage that I'm going to try to backfill. Again, I'm trying to work up to the stage of having 26s and 19s. So I'm pretty far away from that still, and you're going to see that I'm going to have to do this a few more times. But the idea is that anytime I see 5s emerge, I'm going to have an ability to actually convert those 5s into something. Likewise, once I see 7s emerge, I'm going to have an ability to convert those 7s into something. So for right now, I'm going to work with those 5s. Even though you can see that I have a 7 right here, I'm going to work with that one last. So I'm always going to work first on the 1s, then on the 2s, then on the 5s, then on the 7s. So working back as we go. So in this case, what I want to do is I want to solve this thing for a 5. So I'm going to have a 5 is a 19 minus 2 times 7. So you're going to see that backfilling these 5s is going to create some more 7s. And that's okay because we know what the 7s are going to become in this case. So changing that little 5 right here into exactly what I wanted to. So a 19 minus a 2 times a 7. And then there's going to be this negative 2, and that's 7. Distributing that 3 in is going to give me a 3 times a 19, which is good. You're going to see these 19s start to creep into play, which is what I want to see up above. And then the 3 and the negative 2 is going to make a negative 6, and that's multiplied by a 7. And then this thing is just kind of hanging out at the end. Last but not least, I could combine those two things to give me 3 times 19, and this is going to be minus 8, and then it's going to be multiplied by a 7. All right, we're good so far? You can kind of see all those little processes coming into play. We're working backwards in this case. We first attacked the 2, then we attacked the 5. Now we're going to try to attack that 7. So this is where we're going to use that last line of this equation. We're going to look at this component right here, solve that thing for a 7. So in this case, I'm going to have a 26 minus a 1 times a 19. And now I'm going to have an ability to actually kind of replace all of those 7s with something else. So in this case, that something else is going to be 26 minus 1 times 19. So in this case, going back to this little 7, I'm not going to touch that first thing right away. There's a negative 8 here, and so here's where I'm going to replace, what was it, a 20, go back and check, 26 minus 1 times 19. So a 26 minus 1 times 19. Okay, so now I'm going to distribute that little negative 8 in, and then you can see that I'm actually going to be done at that stage because everything that's going to exist are going to be 26s and 19s. So that's really nice to see. So in this case, a 3, a 19, a negative 8 times a 26, and then here's going to be a plus 8, and then multiplied by a 19. So in this case, excuse me, I have my two things that happen to have 19s with them, so I'm going to kind of go back up here. So this stage I'm going to have a 1 is going to equal, so the 3 and the 8, that adds up to an 11. So I have 11 of these 19s, and then I have negative 8 of these 26s. And if you go and actually compute those two things, you hopefully will see that it does actually kick out a 1. If you take that 26 multiplied by negative 8 and then add an 11 plus a 19, it does actually check out to becoming a 1. So in this case, this is exactly the x that I wanted to see. Whoops, the negative 8 is the x I wanted to see, and that 11 is exactly that y. So in this case, I flipped them around, but that's totally fine because x times 26 is the same thing as 26x. It doesn't matter which way you multiply them. Okay, so now what do I want to do? I want to think about what's actually going on in this situation. I'm going to get some inverses out of this thing. What I know in this situation is that if I reduce this thing modulo 26, this component would actually disappear. So what I get out of this is that I'm going to get 11 times 19 is going to be congruent to 1 modulo 26, 26 with a 2. So that's going to be a nice little thing. Also, if I were to take that equation and reduce it modulo 19, I would end up with negative 8 times 26 is going to be congruent to 1, in this case modulo 19. So in this case, I do get two pieces of information in that I'm going to get a whole bunch of inverses. I'm going to get the inverse of 19 is 11 modulo 26, and vice versa. If I was looking at 11, I know 11 times 19 is going to be 1. If I know one inverse, I automatically know the other one. So I get inverses of two numbers in the mod 26 setting. Likewise, I actually get inverses of two numbers in the modulo 19 setting. We're actually going to be looking at this mod 26 one. Again, this is the one that has this nice kind of affine cipher connection because we know that there are 26 characters, at least in our kind of uppercase alphabet or lowercase alphabet. If you wanted to double it, you just have to up this power a little bit. But for now, I'm just going to deal with these single letters, either uppercase or lowercase, just so I don't have to deal with massive numbers. It's bad enough kind of going through these with these small numbers. It's worse worse once you start adding in the full ASCII alphabet and things like that. So in this case, I do know how to find inverses of 11 and 19. I just got them by doing this extended Euclidean algorithm and going from there. What that gives me then is the ability to actually attack a question like this. So I want to look at how do I solve something that looks like 19x is congruent to 13 modulo 26. So in this case, just like before, I have this little 19 stuck out in front of that x, and I want to think about how to get rid of that thing. So in this modular arithmetic world, I do not have this notion of division, but I do have this idea of multiplying by something that's going to make a 1, which is exactly what you're trying to do when you're trying to solve equations in your arithmetic world, kind of from back in algebra setting. If I wanted to get rid of that 19 in that setting, you want to divide by 19 because 19 divided by 19 is going to make a 1. So it's still in that same realm of trying to get ones. It's just the way that we get ones is going to be a little bit different. So in this case, we're going to use this information that 11 multiplied by 19 is going to create that 1 in this mod 26 setting. So all I got to do to solve this thing is simply multiply both sides by an 11. So in this case, 11 multiplied by 19x is going to be congruent to an 11 times a 13, in this case modulo 26. What's going to happen on that left-hand side is that 11 times that 19, if you actually do that computation and reduce it, you'll again see that it kicks out a 1, or we can just use this fact that we just got done showing that says 11 times 19 is congruent to 1 mod 26. So the left-hand side is going to reduce to that 1 with an x. That right-hand side, if you actually compute 11 times 13, is what? 143. And that's still going to be done modulo 26. And now if you really wanted to clean this up a little bit, you could take this 143, do the reduction modulo 26, and I believe you're going to get something like a 13 out of that. So if you wanted to get down to a stage that's a little bit easier to work with, you're finally left with a solution of x being congruent to 13 modulo 26. So again, this is going to give me a massive list of things that solve this congruence. It's going to start off in a sense at 13, and then you can add 26 or subtract 26 as many times as you want to. In this case, we're going to have an infinite number of solutions to these things. So I do have another one of these examples actually in our notes. I'm not going to run through the whole process because I'm probably going to mess up some negative signs and things like that. But if you're interested in seeing kind of another running of this Euclidean algorithm and this extended Euclidean algorithm, I actually have their version for the pair of numbers 120 and 49. So first off, trying to show that these things are relatively prime is going to invoke this Euclidean algorithm. So this is this forward direction. So you're going to look at the pair of numbers 120, 49, do the division, you're going to see that you get a remainder of 22, and then you rerun it with 49 and 22, you're down to a remainder of 5, and then doing it again with a remainder of 2, and then ultimately you're getting your little remainder of 1, which is exactly what you wanted to see. So in that case, we do know that those two numbers are in fact relatively prime. So yay, they're relatively prime. Then what you want to do is you're actually going to try to find those special values x and y that are going to satisfy this equation of 120x plus 149y. So in this situation, what's going to happen is that you're going to work backwards again. So you start with this equation, which is going to say 1 is going to equal 5 minus 2 times 2, which is what we actually started with up above. Then you're going to take that little 2, which was that last remainder before that 1 occurred, and you're going to replace it with its version of its equation. So in this case, going up 1, you can see what 2 becomes. 2 is going to be a 22 minus a 4 times a 5. So you replace that with that little 2 that you had up above. And then you're going to distribute that little negative 2 and then regroup things at this stage. So now you got 9 times 5 minus 2 times 22. We're not going to worry about the 22 right away. That's going to come into play a little bit later, but you're going to have this 5. That's the next remainder up this tree. So I went from 1 to 2. Now I'm at the 5 stage. You can solve that equation for a 5, giving you a 49 minus a 2 times a 22, and then doing that substitution. So in this case, that 5 is going to become a 49 minus a 2 times a 22. Distributing the 9 is going to give you 9 times 49 minus an 18 times a 22, and then subtracting off again this little negative 2 times a 22. Combining things at that stage, so you have the negative 18 and the negative 2, which is a negative 20. You're now at the stage that you can actually attack that 22, so the next remainder up this tree. Solving that thing for 22 is going to be 120 minus 2 times 49, which is exactly what we substitute into there. Distribute that negative 20 across, and then you're down to the stage of having those fundamental things that you're actually looking for. So again, I'd encourage you to try to go through all the kind of painstaking details of these things. It's really easy to lose negative signs as you go through these things. It's one of these reasons why I'm just going to print this out so I don't have to worry about the negative signs, because I'm inevitably going to make a mistake. I did try to keep these somewhat color-coded, so you can see this little 1 was my first remainder. Then I have this 2. then the 5, then the 22, and then all these things in green are actually the things that I'm ultimately hoping to get down towards. So the idea of 120 and that 49, those are where I'm working towards. So once I see one of those, I'm going to just freeze it. It's there. It's just kind of coming along for the ride. So in this case, my x ended up becoming a negative 20, my y becomes this negative 49, and at that stage I could actually do whatever amount of modular arithmetic I wanted to actually see some kind of inverses and things like that. If I did a reduction modulo 49, you could see that I'm going to have a negative 20 times a 120 is going to be congruent to a 1, in this case mod 49. Likewise, if I did the reduction modulo 120, I actually get that 49 times a 49, which is actually kind of a neat little thing because it's its own inverse in this case, is going to kick out a 1, in this case modulo 120. So that's the idea that's going on in this case, is that once I do this full-fledged extended Euclidean algorithm, I'm going to get these special values of x and y, and from that I actually get information about what these inverses are. So all these processes are going to be kind of complicated because there's a whole bunch of little steps that go into it. You're going to first have to actually show that they're relatively prime, then work backwards, then do this reduction modulo whatever your thing is to get that actual inverse, and then take that inverse and actually solve these things. The actual solving stage is actually pretty easy. All it is just, okay, now I know what the inverse is, multiply, and you're done. Getting to that inverse, though, takes a little bit of effort. You're going to see that there's a few little processes that do come into play. But both of those actually can be coded somewhat efficiently, and it's not very taxing on a computer to actually compute those things. It's much easier than actually having to do it by hand, because a human's inevitably going to make mistakes in this computation, but a computer is very good at crunching through a bunch of these little operators, because really all that's going on is just multiplication and addition and some subtraction, but just making sure you don't lose those things as you go.